Thank you. Thank you for everybody for being here this morning. You're all very brave. And thank you for the ISMRM for having me. This has been a very fantastic first conference. So, to begin, nothing to disclose. And let's get into it. So, as we've heard in several sessions at this conference, spinal cord atrophy is present in a whole host of neurological diseases. And it's of interest as a biomarker for disability. It's reasonably well correlated, actually, with clinical measures of disability in patients. So this makes it a very exciting biomarker for clinical trials, an endpoint in longitudinal studies. And one such method of quantifying spinal cord atrophy is spinal cord cross-sectional area, which I'll call SCCSA or something along those lines for the remainder of the talk. So we've been quantifying atrophy and cross-sectional area in the cervical spinal cord for some time. I know there was a whole session dealing almost exclusively with that yesterday. But new hardware and software developments let us get higher resolution whole spine imaging in clinically reasonable times. But there is a trade-off with this. We have to deal with much more severe effects due to gradient nonlinearity because the spinal cord is such a long and large piece of the anatomy. Very little of it sits inside the isocenter. So we have these kinds of warping effects that are, I'm sure, very common to anybody who's done large FOV imaging before. So this is a pretty severe issue when we're trying to quantify a spatial metric about the spinal cord. So there are unwarping solutions currently available to deal with this issue. They usually use spherical harmonics. You've got the online vendor-supplied algorithms, which are kind of commonly used clinically. You plug it in, and you get your unwarped image. And then there's offline unwarping algorithms, which have been developed by the MR community. Both of them are based upon these spherical harmonics to characterize the field. But you could conceive that an ideal solution, especially for these kinds of trials that are of interest for biomarkers in the spine, would be routine field modeling and centralized data analysis, something more scanner independent, site independent. So this would eliminate bias due to different vendor implementations and local variations in the scanner. We've seen in previous talks, some sessions, that it's quite clear that even between scanners of the same vendor, there could be massive differences at different locations. It addresses gradient drift over time. But this kind of periodic modeling and analysis would require a pretty specialized phantom and manpower. You conceive of some kind of large three-dimensional phantom and somebody to actually run this operation. So what we were interested in doing is taking out the most important aspects of this characterization and building a phantom and a system that you could use a little bit more quickly and easily. So that gives us the spinal spatial phantom. Because the full implementation is very expensive, we've developed a low-cost, easily implemented solution to hit the most pressing problems. So it's a cord length phantom designed for in situ optimization of the Z gradient, which is the primary gradient along the spinal cord axis. It's imaged during each scan, and it does require multiple table positions, but currently so does a clinical whole spine image. It requires at least 2 imaging positions to capture the whole spine, so this isn't requiring any additional imaging sessions. And also, the nonlinearity correction would be based on aligning the phantom structures in each scan. So you've got a little region of overlap, and you want to make that region interlock as best as possible, so you'll have a sense of what that looks like. It's a grid phantom. It was designed in CAD software and then printed using an MR invisible polymer, at least MR invisible to the sequences we were using. And it's a quick and affordable fabrication by virtue of being 3D printed instead of machined out of expensive equipment. It has a 2D grid of chambers that are oriented along the length of the spinal cord, as seen in this side image. And then you've also got, in the CT image, it has a little bit of XY plane grid also. So you've got alignment here and alignment here that we're dealing with. And it's a hollow phantom. You can fill it either with deionized water, which we did for this study, or with some kind of doped MRI contrast, like a salt water solution. So the acquisition, briefly, was done on a Skyra 3T. It was a 3D TSE sequence with neck and spine array coils. The phantom was on the spine coil array, and the subject was on top of the phantom. These are the resolution parameters. Most importantly, the FOV was 320 by 320 by 52 millimeters, and we used 126 millimeter table advancement. So the first scan, then we advanced the table 126 millimeters, and that's because that number is specific to our FOV. It's an integer multiple of the voxel resolution. We did 3 scans versus the 2 that you would need minimum to cover the spinal cord. We wanted a little bit more overlap and accuracy for this pilot study, and we used 3 healthy human subjects. So the way the process works is you've got your 3 scans, and you've got the phantom present in each scan. We then segment and threshold to get the phantom grids to show up. And you can see these 3 colors represent 3 separate scans of the phantom in different positions. And we apply an unwarping algorithm, kind of the initial guess. We use the dice coefficient, which is a metric of overlap between objects, to evaluate how well we've unwarped the image. And then we run a numerical optimization on that coefficient to get new z coefficients, the 3rd, 5th, 7th, and 9th order in this case, and then we reapply the unwarp. And we keep iterating through this until we get a nicely aligned segmentation of the phantoms, and the dice coefficient is minimized. So this is the actual data. Briefly, let's go through the key. We've got these different colored points and lines representing the measurements, which is the cross-sectional area of each region of the spinal cord. And these lighter lines of the same color represent where the isocenter was for each table position. So we're taking the isocenter to be the ground truth, the most accurate cross-sectional measurement in this case. And these are our 3 subjects. On the top is the default offline unwarping, and on the bottom is our optimized version of the unwarping algorithm. So just to highlight some regions that were particularly look particularly good, we've got in the first scan we've got these 3 positions, each hitting the same region of the thoracic vertebrae, and they don't really line up at all. There's no continuity between the lines. After our unwarping algorithm, we've got a much tighter grouping of the points, which we take to be, if nothing else, a sign that we've unwarped. Whether or not we have ground truth, well, I'll discuss that later, but we've definitely unwarped and aligned the images that were not aligned before. And this is another example, not quite as good as the first subject, but between the green and the blue, you can see a little bit more agreement between the points. Now, another way of looking at this would be the absolute difference. And again, if we assume that the isocenter, these lines, is the best metric of actual spinal cord cross-sectional area, we would expect to see between our optimized algorithm and the default algorithm a bit of a U-shape, which is what we see on most of these scans. As we move away from the isocenter, the difference between the optimized and unoptimized scans becomes greater. So to conclude, we've got a phantom with a self-consistency criteria. It makes it independent of scanner-specific unwarping methods. Using a numerical optimization, we can hone in on our unwarping algorithm and find the best possible fit and the best possible alignment between scans. The phantom and algorithm are designed in such a way to be easily implemented to facilitate ease of use and cross-site standardization. And some future work, as I mentioned, we don't have a dimensional ground truth yet. We're using the isocenter as kind of a stand-in for what should be the best. We do want to go back and validate these tests again with something that we know is of an absolute structural size, and make sure that what we're unwarping is actually, even if the images align, are they the ground truth for what the anatomy is. Also, improving the optimization strategy. There's concerns of hitting some local minimums instead of global minimums, and the same for the segmentation. In some cases, just to go back briefly, we don't see a U-shape in some of these graphs, potentially because the segmentation is actually introducing more spatial errors than the gradient non-linearity. So that's something we have to go back and examine as well. And also improving the strength and precision of the phantom design. It can always be made more structurally robust, and we want this to be as straight as possible. So I'd just like to thank all of the members of the labs that helped me with this in the Imaging Institute at Mount Sinai, and also the Rapid Prototyping Center for 3D printing this phantom. Thank you.